Hello, everybody. Welcome back. It is Wednesday evening. Well, it's Wednesday evening on the East Coast of the United States, which means it is time for our weekly ExoLife Hangout. My name is Tony Darnell. I'm from deepastronomy.com, and we do these hangouts each week at this time to highlight our search for life in the universe. And this is a collaboration between deepastronomy.com and the Planets Foundation, which are a group of people, a consortium of scientists and organizations from around the world who are doing some truly extraordinary and groundbreaking work in helping us build ground-based telescopes to find life elsewhere in the universe. And today we're going to be talking about one of those. Well, we're going to be talking about the whole program in general, but also in particular, we're going to be looking at the Colossus Telescope, which is an amazing ground-based telescope, which I can't wait to learn more about myself, but also to discuss with you guys. So let me go ahead and introduce my guests. Joining me from the Planets Foundation, Dr. Jeff Kuhn. He's a solar physicist and astronomer at the University of Hawaii also, aren't you? Yes. So that's where you are right now. And also Dr. Svetlana Berdyugina. She is currently in Germany. Hi, Svetlana. She is also a solar physicist, right?
Yes, I'm solar and stellar, yes.
Solar and
stellar. And exoplanetary as well.
Yeah, you guys, I don't know what it is about solar physicists, but we like to think outside the box. I worked in solar physics for about 13 years, so I know a little bit about what they're doing.
It's a good thing. It's a good field to start because you're prepared to do physics in astrophysics.
That's right. Okay, so that's it, and there's also some exciting things happening in that field as well, but that's not the scope of this. So here we go. We're going to. Jeff and Svetlana and Kevin and I were talking before the hangout started about the way we wanted this particular hangout to go, and Jeff reminds me of these points that I don't think about often enough. If you've watched any of my videos for any length of time, whether it's the astronomy videos or the hangouts or Space Fan News, whatever it is, you know that I've been saying over and over again, we live in the golden age of astronomy. Never before have we had so many wavelengths available to us to explore the heavens, whether it's the deep infrared for galaxies that are very far away, the ultraviolet with the Hubble Space Telescope. We live in a time when the universe is wide open to us in so many ways, and we've been exploring a lot of these wavelengths using space-based telescopes as well as ground-based telescopes. Which Jeff reminds me, and I think this is a good point to make, that, they're kind of old school. We are on the cusp of a golden age in ground-based telescopes. And so I want to have Jeff expound on that just a little bit. What do you think of that, Jeff?
So the exoplanet problem is one that depends on having a telescope that, first off, is, we say, diffraction limited, which means that it takes full advantage of the size of the telescope to produce images of the utmost, we say, angular resolution, the fine detail. And that's because we have to separate something that's a billion times fainter than the star, that's the exoplanet, from the light of the star. And so what the Planets Foundation has been doing, and by the way, this is a group of scientists that's been around together for about 7 years. It's a group that involves scientists from Germany and Brazil and Japan and France, and we're all pushing the notion that we got to get beyond this sort of Keck era of building telescopes. So there was an era of time before the 1980s, let's say, which a good example of that were the Keck telescopes, where we made telescopes out of a single big mirror, and the mirror was thick enough so that it was stiff and it could hold its shape as you moved it around in gravity. And then there was this next era where the Keck telescopes, and you may know that the Keck telescopes are actually, excuse me very much, sorry about that. The Keck telescopes were constructed from lots of segmented mirrors. And so here the idea is that instead of using glass to make the mirror surface hold its shape as it moves around and as the wind blows on it, we use a steel structure in the background, a steel backing structure to do it. And that allows us to make mirrors that are much less massive. Why is the weight important? Well, it turns out that if you look at all the telescopes that humankind have built, 'the cost of those telescopes turns out to scale it increases as they get heavier. Now, some are cheaper than others because they don't have to be as stiff, but basically it's the stiffness of the telescope for doing optics or radio or whatever, and the weight that matters. And the Keck telescopes, starting in the 80s, were a big step in that direction because we could take the thick glass and we could replace it with steel, and we could make, we call it a truss structure, like the open structure on a bridge, and we could get the stiffness without having all the extra mass. Okay, so that's a great thing. The bad thing in that Keck era of telescopes is that there are lots of little pieces of glass, and every piece of glass has an edge and a corner, and it has to be aligned, and the whole surface has to make a single shape that's accurate to a fraction of a wavelength, because that's what a telescope has to do. It has to have a surface that's accurate to a fraction of a wavelength. It's a really tiny number. It's 10 millionth or less of a meter. That's why telescopes are hard and why they're expensive. But since the Keck days in the 80s, lots has changed. For example, we now have information technology and the ability to mass produce electronics. And it's possible to make mirrors that don't have mass that make them stiff, but have actuators that have, if you like, in this new world, they're called artificial muscles. Actuators and sensors that allow you to push and pull on thin pieces of glass to make them have the right shape. So they effectively seem like they're stiff, but they're not stiff because of all the mass that goes into these telescopes. So that's the idea, that in this new generation of building optics, we should replace mass with intelligence or with information technologies.
Okay, I like this analogy with muscles. Let me just go.
Sure.
Like bones and muscles, we have to support the body. Before we just had bones. Now we've tried to get muscles in work.
Yeah, we're going to make muscle mirrors. That's right. That's
no bone. Well, there are still some bones to support it, but mainly muscles, as I understand.
Okay, so I want to go back before we get too far down this road, because you said a lot of things, and I let you say a lot of things because I was also looking at all the different channels here that I'm making sure I'm up and streaming. I just want to give a quick note to everybody that I am looking at Facebook, YouTube, and Twitch, as well as Periscope, to look at your chats. And so we hope you guys will get involved here as we get going. And I'm reading those chats. So is Kevin, and we're both going to read your questions and comments out as we go along. But Jeff, you said something I want to go back to. You said something about diffraction limited telescopes. These are telescopes that are limited in what they can see by basically the optical components themselves and nothing else. There are many things that can inhibit that can limit what a telescope can see. For example, diameter. Telescopes that are only so big can see certain things. What are some other things that limit telescopes besides just the optical components themselves?
Yeah. So the main thing that's changed since we were building telescopes in the Peak era or in the Keck era is that we now wouldn't think of building a telescope without what we call adaptive optics. So adaptive optics controls or mitigates for the blurring effect of the atmosphere in front of the telescope. And of course, that's part of the argument for going to space.
Okay, but those correct for a limitation in the telescope, but what limitation is it correcting for?
It's making the telescope diffraction limited.
But it's because the atmosphere is in the way, right?
Because the atmosphere is in the way.
That's another factor. That's what I was trying to get you to say. The atmosphere is another thing that limits what we can resolve in a telescope, and that you could see it if you've ever been outside on a hot summer's night like tonight. You go outside, you try to look at the stars, you'll see they're just kind of boiling because that's what the atmosphere is doing. It's just turbulent, and that's what Jeff's is saying. That is what gets corrected for. If you have too much of that going on, telescope can't see anything. The object, I don't care what it is, gets smeared out. You could have a 20 billion meter telescope, and it's going to get smeared out if the atmosphere is crap. So this is an important part, and that was like during the Keck era that Jeff was talking about. So it corrects for the atmosphere. We've got go ahead, keep going.
So the other limitation, once you correct for the atmosphere, is that all of those little mirror segments have some sort of an active system, and it works pretty well, but it has residual, we call it residual noise, mechanical noise, and that mechanical noise translates into So think of you're on the coast, and here comes a wavefront, and you see a nice straight line. The actual surface that may reflect that wave going back out onto the water can be curved, and so when it reflects off, the wave will take the shape of the surface that's reflecting it. When you have a mirror and it doesn't have the perfect focusing shape, so the mirror is a little different than the coast, because the coast, if it were a straight line, the reflection of the wave would be just back out. But in a mirror, we actually want the wave to converge and to look like a circular profile, so the energy comes to a point. That's what the telescope does. It's a concentrator of energy, and the point that it brings the energy to, you want to be as small as you can so that you can see waves that come from different directions. So, go ahead.
And I don't want to get bogged down in what these adaptive optics are, but it is an important point for what we're going to be talking about later. So I think it's important to just dive in a little bit more. When these wavefronts, when you just think for a second what this telescope is doing, folks. A light from a star hits the top part of the atmosphere. By the time those photons get from the top of the atmosphere down to the telescope has to see that, correct for it, and cancel out any of the distortions that the atmosphere is doing, and it's traveling at the speed of light or close to it, whatever the speed of light is in the atmosphere. It has to do it in a blink of an eye, right, Jeff?
Absolutely. The atmosphere is changing in time, so you got to build something that not only senses how the atmosphere distorted that wave, but then you got to take a mirror that undoes that distortion, so that when the energy is focused back, it's still a perfect focus, at least to the limits of what we call diffraction. But the point is that now in this era, we do that, and we build telescopes that are diffraction limited.
So I think I know what you're going to say, but and Svetlana, you can comment too, but do you think, now that's the big advantage, folks, of a space telescope. When you're in space, you don't have to have adaptive optics. You don't care. There's no atmosphere to correct for. Do you think that adaptive optics are good enough to make space telescopes obsolete?
It is very good, yes. And we reached the level that we can correct for the atmosphere pretty precisely. And on 8-meter single dish telescopes, it's shown, yes, it's demonstrated.
So they're just as good. Every bit of pound for pound, inch for inch, or millimeter for millimeter. They're just as good as space telescopes. Is that?
Well, but we have to. Okay, so there's some other subtleties in this, right? As you know, the space telescope is working up in a very cold environment, and
right.
So you have the advantage of the thermal energy that comes from a ground-based telescope. Doesn't exist for a space-based telescope. But I was going to add that even though you have a space telescope and it doesn't have an atmosphere, the other problem in these multi-segmented telescopes is that those mirror segments, they vibrate, they move. It's a structure that is composed of individual segments that have some way of putting them into place and holding them in place. And so there's a vibrational energy that causes the mirror itself to change its shape in ways that you don't necessarily want. So it's not true that from a space telescope, when you go to the utmost limits of a diffraction-limited optical system, that you may still have to have a wavefront correction scheme to take out the effects of this segmented optical system. And of course, there are limitations to your ability to measure that and to take it out. And so the point of, let's see, there was another point in here, which is that what matters for the exoplanet problem more than anything else is, first, it has to be diffraction limited, and we all agree we can do that on the ground. But the other thing is the size of the system. The size of the system, so the number that matters is the diameter of the telescope to the 4th power. The sensitivity of seeing a faint signal in the sky, think of it as the integration time. So the integration time.
That's the amount of time you're collecting light.
Yeah, that's the amount of time that you're collecting light to be able to detect the signal. In a telescope which is diffraction limited and which has some background light, whether it's the atmosphere light, scattered light in the atmosphere, or whether it's light from the zodiacal dust in the solar system. But the time it takes to reach a certain level of sensitivity scales like 1 over the diameter of that diffraction-limited optical system to the 4th power, at least as fast as that, sometimes faster. So if you took a 2-meter telescope in space, a diffraction-limited telescope on the ground, which is 2 meters, would be two times, well, let's do it this way. Diffraction limited telescope, which is 10 meters in space, would be 10 to the fourth, would require an integration. What's a good example? On the ground, on the ground, a 1 meter telescope has a sensitivity that scales like one. It takes 1 unit of time to be able to detect an object. In space, that number is to get that same sensitivity requires something that is 16 times larger, effectively. In other words, that's not a good example either. Let's take the LUVOIR. LUVOIR is a space telescope, and suppose that
proposed telescope.
It's a proposed space telescope to do these kind of studies. And LUVOIR is about 8. It has a
12. Well, it's not decided. It's like, say, 12, 16 they talk about, something like this, yeah.
Yeah, I didn't think it was quite that large, but let's suppose it's 10 meters. Mm-hmm. The 10-meter telescope in space would be I think what we ought to compare, and in fact now I have to put in some numbers for the wavefront of the 10-meter telescope. So let's just stick with understanding that sensitivity goes like the diameter of the telescope.
It's proportional to the diameter of the telescope. And this sensitivity is important because you can't be looking for signals for a very, very long time, impossibly long times. You want to keep these things for as short a time as possible because you have other things going on while you're collecting photons. You may have noise from your CCDs or whatever going on. So you want to minimize the amount of time that you are looking at an object as much as you can. So diameter is important. It's huge. But I want to... As to go back to this point of the next era of ground-based telescopes, and then I want to move on to the telescopes we're going to talk about in particular. So back in Galileo's time, and in Herschel's time, and in the astronomers, they would build these telescopes that had a piece of glass or whether it was a lens or a mirror on it. And that was just one of them. And we kept building them bigger and bigger. We made bigger refractors. We made bigger mirrors. The Palomar mirror in California is 100 inches in diameter, and it reached one of the pinnacles of a single piece of glass that what you could do with it. But it was heavy. In fact, glass, if you move it around a big enough piece of it enough, it actually flows. There's an old story about the McDonald Observatory in the University of Texas. An astronomer had gotten somehow upset, or somebody had gotten upset. I don't know how the exact the folktale goes, but he fired several shots into the primary mirror of the McDonald Telescope in Texas. Those bullet holes are still there. It did nothing to it. Didn't break. It didn't explode. It didn't crack. It just opened, and the holes are still there. So it acts more like a liquid than a solid at certain points, but it's heavy and it's thick. And in order to be able to hold its shape, which is hugely important to be able to focus light, like Jeff said, they're energy collectors. In order to do that accurately, no matter how you point it, it has to not flow around all the time. So they solve that, in part, by breaking it up into little tiny pieces. So you've got the Keck telescope, which is one of the most famous ground-based ones. Little tiny, not little tiny, but hexagonal segments all over that make this really huge, relatively lightweight objective. And if anybody has ever looked at the James Webb Space Telescope and Keck side by side, you're going to see some similarities. The colors might be different because JWST is an infrared scope. But that was one of the ways. They had to fold JWST up, and they had to be lightweight, and it had to be big. And so they segmented out those mirror blanks. They made them out of beryllium, which was a very lightweight metal. So that's where we are now. But Jeff is saying, and Svetlana is saying, and I can see this, we're reaching the limits of what those kinds of telescopes can do for us, which means that we need to move to the next level. What are we going to do? And we are already building, and I want these guys to comment on the 30-meter telescope and the extremely large telescope that are being built now, But that's gonna, I think, isn't that kind of the upper limit, Jeff and Svetlana, of that telescope design, or would it be the ELT and the, what was the other one? LSST?
Yeah, I maybe want to finish a little bit Jeff's idea, what he was talking about, that when you have a segmented mirror and they are slightly misaligned, what you have, this misalignment is imprinted into that wave, which can be bigger than the effect of the atmosphere. So we learn how to correct for the atmosphere, but we still have that imprint of the structure of the mirror into the wavefront, and that's what we see in Keck telescope. And we will see that in all segmented telescopes as well, which is not possible to correct, basically. And the design of the telescopes that we promote in the Planck Foundation can get over that, because Jeff probably will continue on that, but I want to say that design allows us to have a combination of a primary and a secondary mirror, so as a single dish telescope. So we'll take advantage of a single dish telescope, which doesn't have that effect of the segmented mirror, and we combine those telescopes into an array. Maybe Jeff wants to continue.
So another way of saying that is let's combine. So an interferometer is a way of combining light over larger distances to get some of the advantages of a bigger, that d to the fourth advantage. It's not quite that way because it's two independent dishes. But if you take the idea of an interferometer and supersize it a little bit by having lots of mirror segments that are each independent telescopes effectively, then you can get a lot of the advantage of having just a single dish, along with the resolution that you get with something which is big, like an interferometer. So, Kevin, you have a picture of Colossus that
yeah, so we do reach that limit, what Tony, you say, that we cannot build single dish telescope of 30 meters or 40 meters and so on. What we have now, maximum 8 meters, what we achieve. But there are so much advantages with the single dish telescopes if we want to use them, and that's how we bring these advantages together. We put these single dish telescopes, many of them, in one array.
Okay, so
okay.
This...
Well, hang on though. So the idea, before we go here, the idea is that the problem with Keck is it has all these individual segments that make up a primary mirror that collectively make a one single telescope. What you're saying, the difference between a Keck segmented mirror primary telescope and this kind of telescope like the Colossus is that you're taking several complete individual telescopes by themselves. Any one of them by themselves is a complete telescope, its own primary, its own secondary, and you're adding those together. Am I visualizing this right?
Yeah,
yes,
you are.
and advantage of it that we do have single dish telescopes there.
And
so
we do.
I've got Kevin's thing up. Let's talk about that then. So
Okay, so it looks kind of like a segmented telescope, but in this case, we don't really care about the gaps. And each one of those mirrors in the Colossus design is as big as you can make it, so that the amount of edges in glass produce diffraction, and they put light in the wrong place. So if you have a bright star and you're looking for a faint planet next to it, we call this the diffraction. The edges of all of the mirror segments produce a background light, and it has structure to it that interferes with the ability to find a very faint object next to the star. So in this picture, each one of these primary mirrors on the right,
the circles on the right.
Yeah, the circles on the right is an 8-meter mirror, and it illuminates a single, very small secondary. So as you can see, astronomers call this, you see that where all the light comes together from the primary segments. That's the prime focus, and then it spreads out a little bit and it goes to a secondary.
Now wait a minute, Jeff. This is the Keck. I'm sorry. This all goes straight into one secondary.
Okay, well let me explain the difference. In the Keck telescope, you care about all those edges, and they all have to line up. In this telescope, we don't have to line up all of those mirror segments. Also, each one of the Keck segments.
But wait a minute, they were all pointing at one.
No, but it's not one single secondary.
Here's a picture of Keck.
Okay.
Not
those are
one single
segments.
secondary in Colossus.
All right,
In the Keck, it is single secondary, but on Colossus, it's not.
So what happens is each one of those segments illuminates a big part of the secondary mirror. And what you have to do eventually to correct the mirror errors is you have to do it after the light comes off of the secondary. And in the case of this sort of interferometer design, Kevin, if you go back to that image of the secondary, maybe we can explain how the secondary works.
Yeah, because I think what I'm not visualizing it properly, because to me this looks like the Keck. So in the Keck instrument, you're all of the primary segments are helping make the image brighter, and you're collecting the signal and putting it on a single secondary. You're saying that it's all of these are going to different parts of the secondary, and then it's that signal that's getting collected?
Yeah, Kevin, show a picture of the secondary mirror segments.
Yeah, Kevin,
just
if you can show
One
secondary.
Oh, okay.
Sorry.
So the difference, Tony, is that you now have the ability.
Yeah, this one.
Because each one is separate. So here's a picture that shows the illumination from every one of the.
And that's the secondary mirror.
It's actually many secondary mirrors. There's a secondary mirror for every one of those mirror segments.
Okay.
It
Thank
is
you.
array of secondaries of those single dish telescopes.
So each one of those secondaries, those circles, is matched to a segment that we saw in the other picture.
Exactly.
Yes,
Got it.
exactly.
And they're small enough that you can use each one of those segments to, we say, interferometrically combine the light from all of the mirror segments down at that final focus near the vertex of the optical design.
So interferometrically, meaning that you're working with the interference of the light waves themselves to build they're interfering. They're constructively interfering with each other. Is that what they're doing? They're getting brighter.
They are, and that's effectively what the Keck telescope does, but it does it with all the errors between each one of the mirror segments. So the other thing that we didn't emphasize properly was that in this exoplanet problem, it's not just the size, but it's also the ability to control the wavefront to make sure that wavefront is as perfectly diffraction limited as possible, because small changes in that create light that obscures the exoplanets. So first off, I don't want to be bad-mouthing the current generation of Keck-era telescopes because they have a different job. The job of the TMT or the EELT is to look at a big piece of the sky and to look at faint objects, not necessarily faint objects next to bright objects, but imagine that the EELT or the TMT is going to be used to look at early phases of galaxy formation. And it has to have a field of view. It has to be able to see a significant, many, we say, arc seconds of the sky at the same time to do that. In the case of the exoplanet problem, all we have to do is look at a little tiny piece of the sky around the bright star, the central star in an exoplanet system. So we can build a telescope that has, astronomers say, a very tiny field of view, and which has a bright star always in the field. And now the other great thing is that because you always have this bright star, relatively bright star, the central star of an exoplanet system in the field of view, we can use that starlight to do the information technology, to do the processing that we have to do to make the interferometer work. And that's the magic of thinking about a different way of building telescopes that are specially designed to do direct imaging of exoplanets. The TMT and the EELT are telescopes that have to serve a broad community of astronomers that are looking over many different problems with different requirements. The direct imaging exoplanet problem has this really amazing property that there's always a bright star in the center of the field of view, and that it has this enormous requirement on controlling the wavefront and getting a big telescope.
Okay, so it's important, and I hear you, that it's important to build the telescope to match the problem you're trying to solve. And in this case, you're saying this isn't just a point and shoot, wide field, general purpose telescope. This is a specific use telescope. And what's required for exoplanet studies, and in particular studying the properties of exoplanets around planets around other stars, is that you need a narrow field of view, among a great many other things. But the field of view, can you give us an idea what kind of field of view we're talking about? For example, the Hubble Space Telescope I always describe has the field of view of a grain of sand held out at arm's length. That's how much of the sky that the Hubble Space Telescope observes when it's taking a picture. Can you compare it a little bit with that, maybe?
So if you take that grain of sand and instead of holding it out at arm's length, you put it across the room for sort of a standard size room, then that's about the field of view that you would see. Or don't take a grain of sand, but take the thickness of one of your hairs at an arm's length. The total field of view that we need for the exoplanet problem and for these kind of optics is 1/100th of the field of view of a Keck style optical telescope.
God, that's pretty amazing. Okay, I want to talk about that some more, but I'm seeing a lot of really great comments that's relevant to what we're saying, so let me get them in here. Bill Druin is commenting on YouTube, and consider the Hubble deep fields. Those exposures lasted days and weeks, no downtime for daytime. Well, actually, they didn't do it all consecutively, but your point is well taken. The integration time of a telescope, it needs to be minimized as much as possible. You can't be doing, there's lots of other issues with looking at something for, let's say, 100 seconds or an hour at one time, and the sensitivity that Jeff was talking about earlier, it helps address that. So that's a good comparison. Although the Hubble has a 90-day orbit, so you had that's the most one, or a 90-minute orbit, and that's the longest it could expose at one time anyway, for a lot of other reasons. So and the Cosmic Stardust is asking, what are potential options in terms of future telescopes? What other materials are up for debate? A lot of this, Jeff and Svetlana, I mean, you correct me if I'm wrong, in part it's a materials issue, and then another part it's a design issue. But are we on the verge of new materials for these kinds of telescopes to be built?
So we need a reflective surface that's stiff enough that we can support it, and it doesn't continuously create problems when a little bit of wind blows against it. There are several ways of doing that, but in the Colossus design that Kevin had up, I don't know if it's still up there, but
what has he got up? He's sharing something else now. This is the rendering.
This is a picture of a telescope that has, it's sized, so each one of those interferometers is an 8-meter mirror with a secondary which is about 15 centimeters across. So it's really a remarkable optic which is dominated by those 8-meter mirrors, and there's a bunch of them. Each one of those, and we've decided, could be built out of window glass. And the tech. So here's the issue of other materials. There's so much development that has gone into glass because it's an architectural material and because its properties are very well known, and it's so cheap and abundant that I think for a long time we're going to be making mirrors out of glass, but very thin glass that's just a few millimeters thick. And the area where the new technologies are important are in the muscles that gradually and gently change the shape of that big mirror. And a mirror which is 8 meters across for our telescopes would have maybe 5,000 or 4,000 of these little muscles on the back surface of the telescope, and you can think of them as little barnacles that produce a slight amount of force that shapes the front surface of the mirror, which has a reflective coating on it. So glass is a really great substance because it's hard, and its properties are very well known, and it's cheap to manufacture. And if you don't rub on it, so mirrors are made now and have been for hundreds of years by grinding the glass and by grinding it away. And the mirrors that we're talking about, you would never abrasively polish. They would be shaped by a process that involves heating them up, but not making them liquid, just heating them up. It's called a slumping process, and then the barnacles on the back are polymers. And there's been enormous work, especially in the 3D printing arena, of creating muscles and force sensors out of polymers, and then voltages that are applied to the polymers. So we have a program with a group in Lyon, France, that has created an amazing polymer, which is 100 times more powerful for the same voltage at producing forces. These are the muscles that go, artificial muscles that go in the back of the mirror. We're convinced that's the future, and it's to use these sort of dynamic muscles to create a mirror which has the right shape optically, using the light which is available from the bright star that's always in the field in exoplanet studies.
So, if I can a little add here. So, yes, it is glass, but with these muscles, if you want, it will be different material, combination of glass and muscles. This will be kind of a new, what we call metamaterial. So, that's where the future is, we believe, that it's not traditionally just glass, but it's combination of, say, polymers, what Jeff described, and glass, and that what makes a new material, a new metamaterial.
And so if you think about why this is possible now, it's in part because we have this what's called additive technology, 3D printing. It's possible to make things that are complicated, have lots of pieces and wires and connections by computer, and over very large scales, to make a big 3D printer. So, for example, if we were making this telescope, we wouldn't make the mirrors someplace else. We'd make the mirrors at the location. Maybe we ship the glass there. Maybe we even float the glass on. It's float glass. It's simple to manufacture. And there's no transportation of these big mirrors, part of any.
Which was a challenge back in the day. You can always see historical pictures of places like Palomar where trucks or even some cases mule teams were used.
Donkeys.
Yeah,
Right.
exactly. So good. Okay. Well, I want to get some more questions. Kevin, you were trying to highlight one for me. You want to just read it?
Yeah, Abdul asked a really good question. So
okay, go ahead.
In the description, I was talking about that Colossus will be able to look at the nearest 300 stars, and he was asking, nearest 300 star systems, are you talking about sun-like stars only? Does this mean that it's not optimized for red dwarfs?
No, it is actually with red dwarfs as well. We expanded it to several hundred, which Colossus can observe. This will be the planets around stars from spectral class like the Sun. It's a G class, and then K, a bit cooler class, and M as well. So all these three types, and F stars, of course, they are also brighter. So this kind of cool stars, spectral classes, we will cover them.
Okay. So, in fact, let me just amplify a little bit. The current telescopes, even the EELT and the TMT, are struggling, will struggle with the M dwarfs, because in the M dwarf problem, the exoplanet is getting closer, the habitable zone is getting closer. So the interesting exoplanets around M dwarfs have a small distance, and it's that small distance which stresses the ability to. I mean, it's a resolution problem. They're close together, and so that's what requires the very large diameter telescope to see them. And in fact, the prototype for Colossus we call it ELF, the ExoLife Finder, and that has a diameter of about 20 to 25 meters. It's a ring of telescopes specifically designed to be able to see the nearest star's exoplanet, Proxima b, and it requires that size to do it. So, part of the answer to your question is that for the M dwarfs, that's especially the reason why we have to have larger ground-based telescopes.
Well, while we're on this topic, let me just get Abdul Qadir Almami's question in. Is the Colossus telescope, since it's more, if the Colossus telescope is more optimized to look for exoplanets around dwarf star systems, such as TRAPPIST-1, or for sun-like stars? So I guess we've answered part of that already, but what will it show us with systems like TRAPPIST-1 around dwarf systems?
TRAPPIST-1 as well will be available for us. It's within the reach of Colossus. So TRAPPIST-1 is a 40 light years away, and it should be available for Colossus as well. I mean, resolvable.
And did you answer? Because sometimes I'm reading the questions, I don't always hear your answer. Is Colossus more optimized for dwarf stars or sun-like stars? Is there a particular star that this is well suited for?
So the way to answer that is that Colossus is the only telescope that will be able to see M dwarfs, and earlier type stars, G type or F type stars, will be able to have the same sensitivity even further away from the Earth. So it's not that we've lost sensitivity on G stars; it's that when we build a telescope which gets bigger and bigger, the reach of the telescope for seeing and imaging and creating synthetic images of the surfaces of exoplanets gets further out for the G-type or the earlier type stars. Yeah,
because they are brighter. We're kind of magnitude limited, so that if you go to brighter stars, and then you have more photons. And if you go to more luminous stars like G stars, then the planets in the habitable zone, they're further away. So we have this definitely advantage with bigger telescopes.
Okay, and Nicholas Hernandez is asking, is it safe to have a tiger next to a telescope? Nicholas, it's not safe to have a tiger next to anything, including a telescope. Okay? All right. ADW, will there be a new visual light telescope after Hubble? I keep seeing a design for a future one similar to JWST with a larger mirror array. Just very quickly say, visible light, not so much. Almost everything is either in the UV or the infrared that they want to send out into space, because that is the future of the space astronomy, is actually in the infrared. Some UV, but mostly in the infrared. People are complaining about my mic. Is this better? Because, I have this auto correcting thing that keeps reducing my volume. So maybe if I put my mouth closer, it sounds better. Please let me know. Otherwise, I have to keep turning my mic volume up because this stupid Mac keeps turning it back down again. Abdul Qadir again is asking, a few years ago, Dr. Jeff Kuhn gave a lecture in SETI Talks, and since then we have found new targets. TRAPPIST-1, cough. Will these news boost the importance of the Colossus Telescope? And I think I understand what he's asking. Is all of this excitement around things like TRAPPIST-1 helping you guys out?
So Kevin has an image.
Okay, I've got it up.
That telescope right there is a mini Colossus, and it's designed specifically to look at. I think the world should have a telescope at $50 million that does nothing but look at Proxima b, the nearest exoplanet to us. We're going to learn an enormous amount. But this telescope won't just look at Proxima b. It will look at a range of other systems, as we said. A star system which is brighter and hotter will be able to see with the same sensitivity that it would see Proxima b further away from us. And so here's a telescope we'd love to get everybody here signed up for to help build. It's something that would cost about $50 million. It's this interferometric design that we've talked about. It would go in the southern hemisphere. It would look at Prox b, and it would open up the window for doing at one point, I know, Tony, on your program, we talked about making images of exoplanets.
Yep.
With this telescope, through the synthetic imaging techniques, we could make pictures of the surface of Proxima b.
Okay, just so we're clear, Jeff, on this picture, this thing isn't shooting rays out into space, right? This is like, it's coming the other way, right? It's collecting them.
Yes.
Kevin, that was poetic license, right?
Yeah, okay. I just want to make sure that's not, because it looks like a weapon, right? It looks like you want to build a $50 million laser weapon. That's what it looks like.
This is not a weapon.
If you let me comment, we really didn't touch the cost of this telescope. So what Jeff mentioned, hey, we talk to community and say, hey, there is this 50 million telescope, which is not a big price check compared to other facilities like TIM-T and ELT will cost more than $1 billion. And when we send telescopes to space, we know like it's close to 10 billions right now. And for 6-meter telescope, yeah. Say what?
When you think about an instrument on the ground and then one in space, the cost scale is about a factor of 100.
Yeah, and imagine you want to send. Sure, we want bigger telescope in space because there is no atmosphere. That you can continuously observe there. Imagine they put 30-meter telescope in space. This will be an unbelievable price. We cannot really do that.
I agree. I mean, just to put this in perspective, the James Webb Space Telescope, $8.5 billion with a B dollars.
Yeah, exactly, close to 10.
WFirst just got hit. With well, they're not getting hit; they're getting audited because their costs are going up to like $3.5 billion. And as people are like, hold on now, whoa, we're talking billions of dollars. And so, by comparison, a $50 million telescope sitting on the ground, looking at things like Proxima b, like Jeff was saying, or doing even these other closer exoplanets.
Well, we can look at Alpha Centauri A and B, which we don't know yet if they have planets. So look, we have 3 stars, nearby stars. And we can discover so much about planets there.
Okay. Cosmic, we're getting some great questions, so I'm letting you guys drive the hangout for a while with what we talk about. Cosmic Stardust is asking, in reference to Larry Keese's question of why do the edges of the hexagonal mirrors, why do the edges of the hexagonal mirrors damaging exactly? Let me go see if I can find Larry Keese. The edge effects of the he says the edge effects of the hexagons are destructive to the signal.
All right, so here's an experiment everybody can do. You gotta have a clear blue sky and the sun has to be out. Go outside, close one eye, stick your thumb out at arm's length, and put your thumb up against the sun, so you block the sun. And most thumbs are about the right size to block the sun.
Half a degree.
On your own risk. Disclaimer.
Oh yes, I take no responsibility.
Don't stare at the screen. Yeah, if you go blind,
so you are not looking at the sun. One eye is blocked, and you're looking through the other eye. And now look at that very edge of your thumb, and you see that bright edge of your thumb? That's diffraction. And every edge in an optical system produces light, which, even though you block the sun, you're going to get some bright light that you're able to see, which just outlines the edge of your thumb.
And you don't want it. You want to get rid of that.
That's what you want to get rid of, because all that light, the exoplanet that we're looking for is at least 1 million times fainter than the brightness of the central star. And so we have to get rid of all of that. Now do that diffraction problem 500 times. Every one of those mirror segments has effectively a bright edge in the optical system. And that light is bad. It's something that is going to interfere with seeing the exoplanet.
And that's what you said at the top of the hangout. That's with diffraction limited. It limits what you can see, right?
And we build coronagraphs. So after we scramble the light of the star with the exoplanet light, we try to correct for it, and that helps a little. But it's much better to design the telescope to the problem that we're after, and that's what we're pushing. That the exoplanet problem is important enough to all of us, right? And suppose we found evidence of channels on Proxima b, or we found the biomarkers of oxygen and other. All of this will be done with a telescope at $50 million, if it's designed to do this problem. And I think that we're trying to raise consciousness that this community deserves its own dedicated system.
Jeff, you had me at new era of ground-based telescopes, so I definitely agree with that. William Bacon is asking, and it's liked by Galaxia, which brought my attention to it, why aren't you using hexagonal segments?
Well, we could use hexagonal segments, but again, the idea is to minimize the amount of diffraction, that bright edge. So we have to make our segments as big as we can. And think of it this way. What's the geometric shape that minimizes the amount of edge to the amount of area?
A circle. So
the edge is bad for us. The area is good for us because that's focusing the energy. The edge is scattering it. What shape minimizes edge to area? And Tony already did the exercise for us. It's a circle, right? A hexagon is worse for this. And in the case where we build a telescope out of independent interferometer elements, we don't care whether or not they're gaps. See, the gaps in hexagons was sort of the stopgap method to filling up the aperture of the telescope. And if you don't care about that because you're now creating the image interferometrically in the sort of hybrid state, then the hexagon has no advantage. And I would add that in building the Keck telescope, there was a huge problem that was overcome through stress lap polishing and iterated, and finally ion beam correction, that whenever you cut glass, which is what you have to do to make the hexagons after it's polished, you create something that doesn't have the exact shape that you want.
I'd like to add a little bit here.
Okay.
Also explain, like maybe we didn't mention that yet. What does it mean interferometrically, combining this light? That if you have a single secondary, like on Keck, and multi-segmented primary, those edges, they have to be aligned within one wavelength that you observe, so that you make the shape of the primary so precise that it is deviations is within one wavelength. When we combine light interferometrically, we don't have to be within one wavelength. We have to be just in phase. So we have to be within that wave, exactly on the phase, to make a very sharp picture. But we can be several wavelengths away, which allows us actually to have this flexibility in the construction. That's what also interesting to. That is what makes this telescope cheaper also compared to others.
Yeah. So the diffraction. So you're building a series of telescopes, each themselves diffraction limited.
Yes.
And you're adding the signal of the entire telescope at a point somewhere down the line, whereas before, and that diffraction limit and the effects from that is less than the effect you would get from a Keck style segmented mirror. Is that what we're learning?
Yeah, by a huge amount.
Okay, by a huge amount, so not insignificant. Okay, King of Cannabis wants to know, is Tabby Star close enough for Colossus? That would be that alien megastructures, KIC 8462852. Do you guys know about that star?
Yes. No, that star too far is in Kepler field, pretty faint. And by the way, there was recently a paper, which I find pretty reasonable explanation to that. You don't need megastructures. This is just suggestion was that it probably a swarm of asteroids on the same orbit as a planet, as we have at the Jupiter orbit. We have Trojans and Greeks, so that these are the groups of asteroids with preceding and following Jupiter on the same orbit. And if we have this configuration around the other star, we will see exactly the same situation. At first, you have very deep minimum from from a planet, and then, as happens in that system, 700 days later, we see like multiple eclipses of from other objects, and that could be just this kind of Trojan's asteroid.
Very well said. I've often said that too. What was going on with the media around that star was driving me crazy. It was like they were following it, and they were trying to figure out what it was, and it just like, is this a Dyson Sphere? Is it all? Well, probably not. No, there's lots of other things that could.
Yeah, and what I like about this model is that it predicts the next eclipse timing, so we can wait and see. Actually, could be pretty. I mean, if it happens at the predicted time, so we know what's going on.
It's called. Yep, that's what science is all about. So I think that's a great. Thanks for saying that. Let's see. Galaxia is saying, "Oh my God, that's my dream." Pictures of the surface of Proxima b. So,
yes,
you guys were talking about this in one of our first Hangouts together, where you guys have an algorithm, Svetlana, where you can actually, I still am blown away by this, where you can take the light variations from the reflections off of these planets and construct a map of the surface. That was just using what we have now. Was that correct? Using that algorithm with the ground-based telescopes that currently exist, or were you talking about using that with ELF or Colossus?
Yeah, you need ELF for that. You cannot do with the ground-based telescope. We tested the algorithm, we developed algorithm, and we tested for ELF, and we argue that ELF will be the first telescope to do that.
Okay, so yeah, if you guys want to see that that hangout, you got to check it out because Svetlana and Jeff and others have developed this really amazing technique for doing this, but they need these telescopes to get it done. And but the ELF by itself is enough. That's just one mirror, right?
Yeah. No, that planets is what we're building right now.
Oh, planet. Okay.
But ELF has.
ELF is the one which we see on the picture now.
This is ELF here. Okay, I'm sorry. Sooner or later, I'm going to get it all right. This to me, it looks like the Death Star. But yeah, this would be what you'd need, the $50 million scale, roughly scope, to do this. Okay. Let's see. I'm just going through and looking. Mic volume fine and stable these last few minutes. Okay. I'm doing what you're suggesting. I'm trying to stay an equal distance from my mic, but I get excited and I got to do like this. So no guarantees, guys. Sorry about that. Galaxia, let's see. Is that a question? Galaxia is commenting, yeah, but that's including technological revolutions. If the same space telescopes would be rebuilt, they would be cheaper. And she's making the point, and I agree, that a lot of these things, when you launch a space telescope, you have to invent a lot of technologies that don't exist yet to make them work. That costs a lot of money. So but still, I think there's still this argument that ground-based telescopes do that too. It's just cheaper all the way around because you're not in space. Sahid is saying, once JWST reaches L2 and fails to open up, the whole operation has failed. Then why can't it open up in low Earth orbit? If it fails, we can repair it like we did to Hubble, then send it off to L2. Wow, there's a lot there. No, even if it were, we can't even repair Hubble right now. If Hubble breaks, we can't go up there and fix it. We've got nothing. We got no ability to send anybody up there to even fix the Hubble Space Telescope. If JWST goes up there and doesn't open, let's say close in Earth orbit, again, we got nothing up there to go fix it. It's going to be a tense moment, but what they're going to do is they're going to start unfolding it way before it gets to the L2 point. And if you look at the deployment sequence videos that Northrop Grumman has built, you'll see it's like 6 weeks it's going to take. By the time it gets to the L2 point, they're going to slowly unfold all of this stuff. So it's going to be a tense time, no question about it. Larry Keese is asking, is there a golden rule for the relative sizes of planets? That's a good question. Do you guys know?
So there was just this week an interesting paper from some of our colleagues that says that planets occur as either mini Neptunes. Did you see that paper, Svetlana?
No.
Howard and company. They went out and they measured very accurately the radii of the stars that have transiting exoplanets in the Kepler sample.
Yes.
And by doing stellar observations, they can get the stellar radius more accurately that gives the planetary radius more accurately. And there's a gap. There's a gap in the distribution of the sizes of exoplanets. On the one end are the sort of rocky terrestrial Earth-like planets that we think of, and then there's a gap, and then there are the mini Neptunes that there are a lot of, and in between there's a hole, and that's obviously a big clue as to how planets form, but it's an interesting observation.
Well, maybe analogy would be like when we talk about stars, that we know that low mass stars are much more frequent than high mass stars. This is just because of formation, and just because of the amount of matter we have in the universe, and the clumps and clouds. So small stars, they are much more frequent. And I think what we find out with planets, it's also that small planets are more frequent than the big planets. So we started to discover exoplanets from hot, massive Jupiters, nearby stars, just because of our selection, of our sensitivity to such planets. But as we discover more and more planets, we find actually fewer of those Jupiter-sized planets and much more smaller planets.
Well, no, this isn't a selection effect. There's clearly a gap in the formation scenario that isn't due to the details of the selection. So I Google.
Well, there is a gap. I haven't seen that, but I mean that it's still there is clearly bias to the in the bulk of planets. There is a bias towards the smaller planets, just because probably it depends on the matter available around the star, and it's easier to make smaller planets than bigger ones.
Okay, so Bill Druin is saying or commenting, edge effects and diffraction limits are concepts that fall in the field of quantum mechanics of photons. That is why they are hard to explain.
All right. We kind of try to explain it. We hope we got it through.
Right.
Well, wait. They're wave phenomenon.
Right.
So if you take your bathtub and you make a wave and you put an edge, stick a plate or something that's rigid in the water, halfway in the water, that has an edge on it, and make a wave with the bathtub, you'll see from the edge of the plate, you'll see a circular wave that spreads out, which is the diffraction pattern created by the edge of that surface in the water. That's not quantum mechanics; that's wave mechanics,
that's right.
And that's probably what he meant.
Yeah.
It's the wave properties of light and or of matter have this peculiar behavior.
That's correct. And what I think you're getting at is there's this business between whether it's a particle or a wave, but maybe that's what he meant. But yeah, it is a wave phenomena, and it is something you definitely want to minimize. It is difficult to visualize, though. I mean, when you see little ripples coming out from the center of sometimes you'll look at a high resolution or a high magnification photo of a star, and you'll see these little tiny circles coming out around the star. Plus, you'll see little spikes coming out from each side.
Right.
Those are that's all the telescope's doing. The telescope is doing all that to the image of the star, and you want to get rid of that. You just want to see the star. And so these guys have come up with a good way to minimize this. So, cosmic stardust. What are some of the biggest challenges that need to be addressed, realistically or hypothetically, when it comes to the telescopes of the future? And I think we'll let that be the last question for today. Anybody want to take that? What are some of your... Let's just apply it to the Colossus. What are some of the biggest challenges that need to be addressed in building these telescopes?
Money.
Okay, that's not hypothetical, but that is realistic, though.
Yes.
Any other? So the materials are there, the design is there. You guys are happy. You just
we have great ideas. We have technology. We have partners. We will start building prototype mirrors very soon, which will like small ones, like this, just to prove that this muscle mirror can be done. And then we need 50 millions to build ELF and a bit more for the Colossus.
Yeah. So, let's talk a little bit about that. Where are we now in the Planets Foundation's efforts? Do you guys want to talk about any ways people can get involved, or there was a Kickstarter for a while, but I think that's over now, right?
Yes.
The Kickstarter was wildly successful. It raised several times more than our modest goal. There's another Kickstarter on its way.
Okay.
And we're interested in partners that want to be involved in the development of these ideas.
And so the best way to get in touch with these guys is go to planets.info. That's their website. They have lots of ways for you to interact and get involved, and I would encourage you to do that. The reason
Planets.life.
Sorry, planets.life. What did I say? Planets.info? Planets.life, because they're trying to find life on planets. That's why that's how I screwed that up. So, yes. So, and the reason I care, and I'm here every week talking with these guys, is I feel very strongly about it, and I want to help get the word out about doing this. So please visit their website, planets.life, and when those new Kickstarters get ready, we will definitely let you know when those, and the details on how you can do it. So this is it. And, I just want to leave with Jeff and Svetlana. We talked about this before, but it really, it just really affected me when we talked about it. In the past, most of the biggest telescopes that we had built in this country and around the world were done from a private group of people. Governments didn't do this, right, Jeff and Svetlana?
It wasn't most of them. All of them.
Okay.
Were built. There was one exception. For a period of time after Palomar was built, the Russian 6-meter was
Soviet
built.
6-meter telescope was built on government money, yes.
Yeah.
And that was the world's biggest telescope at for some time, yes.
And I didn't fully appreciate this until I started working with these guys. And so it is time for all of us to get going, get involved, do it whatever we can. We want these telescopes built. They can do, think about it. Staring at Proxima b, getting maps of the surface of that planet. This is how we do it. And it's going to cost peanuts relative to what it would cost to go into space and do these things. And we can do it now. So, I don't know. I just want to urge you guys to get involved in any way you can. But I'll leave it there. Okay, well, that is it for this week's Hangout, folks. I want to thank my guest, Dr. Svetlana Berdyugina from the I'll just say the Planets Foundation. I forgot the institute you're working at. The Planets Foundation. Also, Dr. Jeff Kuhn, also from the Planets Foundation. We do these every week, folks. Next week, we're going to be talking about something really cool. You want to tell them, Kevin, or do you want me to do it?
Yeah, we're talking about von Neumann probes next week, so really excited for that one.
With von Neumann probes, that's right. It is something that can be done. It is not not so science fiction-y as you might think. So let's talk about how that can get done. We'll have our guests with us, a co-host and our guests to talk about that next week. So join us next Wednesday, 7 o'clock Eastern Time. Okay, well, that is it. I'm going to stop us here. Thanks, Jeff. Thanks, Svetlana. Thanks, Kevin. Great hangout. Really enjoyed it. Planets Foundation, go check them out. Thank you all so much for watching. And as always, keep looking up.
Thank you.
Thanks.